Hello guys, and welcome back to the Ergo Cast, the frontier for satiating your curiosity upon the next-gen DeFi platform, Ergo. Within these shows, we take the opportunity to cover the latest updates within the ecosystem, with the aim of leaving no stone unturned. As mentioned previously, the Ergo Cast is taking a double-edged approach moving forward, with Robert and myself collaborating in delivering each episode. As a rule of thumb, anything we say is not and should not be taken as financial advice. This show's purpose is to highlight the key pieces of progress within the ecosystem, which all users need to know about. Today's show is going to be taking a slight detour compared with previous episodes, where we have covered the surroundings of Ergo. We will be doing this by looking at an idea which is already implemented, non-interactive proofs of proof of work, or more commonly abbreviated as NiPoPoWs. This concept is denoted as a solution for the problem of interoperability, which will be the focus of today's show. Assisting us on explaining this technical landscape, we have exclusive company who is at the forefront of investigating these ideas. Without going any further, I'm passing the baton over to you, Robert, if you'd like to do the honor of welcoming today's guest.
Sure, thanks, Ollie. So today we have a very special guest who I actually believe we have passed in person, I think at IOHK Summit 2019, but we haven't personally met. We have Dionysis from IOHK and other who has done a lot of research into blockchains, some NiPoPoWs. I know he has some up-and-coming papers, which we may or may not talk about in this call. And so I think this is a really exciting place to explore, especially since in the blockchain world, the last 2-3 years, we've really gotten to the proof of stake side of things, and everyone's really pushing in that direction. However, there's still a lot left to be uncovered, and NiPoPoWs are really one of the novel pieces of tech that are finally being implemented, and they're not just random papers scattered somewhere in academia, but they're actually being put into blockchains, and now we're gaining the tools to use them, build actual new systems, new protocols on top of these, and so we can do stuff like cross-chain compatibility. And so I think in this episode, we're going to get a lot of really cool, nitty-gritty technical details. And so if that's really exciting for you, I think this episode is going to be really jam-packed with all that.
Great. Kicking things off, let's look at the premises which NiPoPoWs build off of, the foundations. Firstly, what makes up a proof for a proof of work? I think explaining this could add a lot of clarity for those who are watching.
So first of all, thank you for inviting me, Ollie and Robert. It's great to be here, as Ergo is also one of my favorite coins. I think it has one of the most friendly communities in the space, and also a clear code base, nicely organized and structured. It's based on very good foundations, and it's exploring some of the most interesting ideas in the space. It stands on the scientific bleeding edge, I would say, on many aspects. So it's an honor to be here to speak about that. And it's also an honor for us that it's implementing our protocols that we designed when we invented NiPoPoWs a while ago. It's one of the coins that implements the concept of interlinking a blockchain from Genesis. So it did not do a hard fork, it did not do a velvet fork, but it implemented it from Genesis, which basically adds NiPoPoW abilities from the very start. So that's pretty great. So to get started with your question on what NiPoPoWs are, what are these proofs? These are motivated by Superlight clients, essentially, even though we have seen now applications on interoperability, and this might be the most exciting ones. The motivation stems from Superlight clients and creating clients that can synchronize very quickly, that can boot up really quickly. And currently, Ergo's full nodes, they take a little bit of time to synchronize if you boot up a new Ergo node. The current implementation of the node is a full node. So if you're booting up for the first time, you need to download all the blocks, you need to validate them. and that takes a little bit of time. For some computers, it might even take a day or so. So the vision here is that given the consensus protocol of Ergo, these proofs of proofs can be used to make this super fast. And this is one of the things that I'm looking forward to being implemented and seeing it in Ergo. I think there is definitely plans to do that quite soon. So that's exciting. So let's talk about what these proofs are. Well, if I'm synchronizing from the rest of the Ergo network and I'm booting up for the first time my node, I want to know whether my transactions are confirmed, and I want to know how much money I have. I also might want to know what are the few latest blocks that constitute the tip of the longest chain. The strategy to do that in a full node is to inquire from my neighbors in the network about their chains, download the whole chains block by block, including their data and transactions, and then validate each part of that locally so that I can deduce what is the longest chain. One improvement on top of that comes with SPV nodes, which were pioneered by Bitcoin. And these are light nodes, although not super light. And in this case, I download just block headers instead of full blocks, and I still validate the proof of work. The question we were trying to answer when we came up with the scientific discovery is whether it's possible to synchronize with a comparable level of security without downloading every block header from the blockchain. So can I deduce what is the longest chain without downloading it? And that's where the name comes from. This is a protocol in which I'm connecting to my neighbors. They are providing some data to me in the form of some strings, and these strings can convince me that some proof of work happened without actually observing it. So it's not sent over the network, but a short representative is instead sent over the network. So that's why we call them proofs of proof of work, because they show that proof of work took place without actually sending it. So that's the motivation there. And these strings are quite short for a blockchain like Bitcoins or Ethereums or Ergos. These will be well below 100 kilobytes. So it's really much faster than doing an SPV synchronization, where even for Bitcoin that has very light block headers, the synchronization takes 32 megabytes at least or more. So these are well suited for very small and lightweight devices with minimal connectivity that stand behind limited bandwidth connections. These could be from smart cards to older mobile phones to mobile computers in general that don't even have any storage to keep the chain. So that's the motivation there, and this is something that we can actually achieve with these protocols. And Ergo has this enabled already at the consensus layer. So while there might not be an implementation of a super light client right now for Ergo, this is something that can be done without any forks. This is already data that is within the chain. So I hope this answers the question of what these are and what they do. But maybe we can speak a little bit about how they look like. What are these strings, and what is exactly that the thing that is sent over the network that provides this proof of work, and maybe to give some intuition about how these super light clients are actually convinced.
Thank you. And so regarding how they look like, is this all occurring within the mining layer of a blockchain? So once the nonce has been deduced for the next block, is this where the proof is derived from? As you said, they string together.
Yes, they do come from the mining process. So the basic idea in a NiPoPoW, at least in the way that we have implemented it in our papers and the structure that Ergo follows, is a notion called a superblock. So superblocks, they constitute samples of the blockchain, samples of proof of work that indicate that some proof of work has happened around them without actually sending it. So let's talk about what superblocks are and how they can really capture this sample of proof of work. When you mine a block, in any proof of work chain, Ergo, Bitcoin, Litecoin, the proof of work equation is satisfied. That's an equation that says the hash of the block header must be below a certain target. And most people have heard the term that, oh, the number of zeros of the hash must be large. And you can see that in the block explorer, the number of zeros is actually large. But if you write it as an equation, you can treat the hash as a number and say that it's below a certain threshold. So it's an inequality. It's required that for block validity, it's required that blocks begin with a certain number of zeros. Let's say that's 10 zeros, depending on the difficulty adjustment. But it so happens that certain blocks just happen to have more zeros than that. It could be that instead of having 10, they have 11 or 12 or 15. So these blocks that have extra zeros, we call them super blocks. They have more zeros that are necessary for just validity. They somehow happened to satisfy this equation too well or better than required. And the reason why this happens is the mining process really is just a random sampling of the hash function by placing in random nonces. So the output of the hash function is really unpredictable. While this function is being trialed, it can happen that sometimes more zeros are added just by chance. So this is not intentional. And mathematically, this is modeled through something called a random oracle, which says that the hash output really behaves like a random output, like sampling from a pseudo-random number generator. So we can really argue about the distribution of these superblocks within a blockchain. If you think about it, if you treat the hash as just a bit string of zeros and ones, and you say, okay, it must start with a certain number of zeros, you can actually calculate what is the probability that I'll have an extra zero. Because when I have the fixed number of zeros that I need, which is, let's say, 10, the probability that the 11th bit will be 0 is just 1/2, because there's no check there. It can be either a 0 or a 1. So that means that half of the blocks in the chain, approximately, will be superblocks with an extra 0. We call these 1 superblocks. And then a quarter will be 2 superblocks, and 1/8 will be 3 superblocks. And these are quite predictable things. We can model them probabilistically. So you can already see if there is a chain that is being mined, a small number of blocks will be superblocks, but these cannot be mined independently of the underlying chain. It's impossible for an adversary to mine these blocks intentionally to be superblocks. The only way an adversary can mine such blocks is by really performing regular mining, by trying out nonces. So if we are working within the honest majority model of proof of work, really an adversary cannot break this protocol because they cannot do anything to superblocks that they cannot do on the original chain anyways, which means under the proofs of security of Bitcoin itself, we know that the adversary cannot fork the chain and create long forks. There will be a common prefix shared between the honest nodes. Given that these forks cannot be created by an adversary, we can also have similar arguments that the adversary cannot create such forks on higher level chains of superblocks. And so these do really function as efficient samples or a sampling method of proof of work. So the idea here is that there is the verifier that is booting up and receiving the chains. There is the prover that is a full node that wants to convince the verifier that this is the chain. So the verifier connects to a couple of provers, their neighbors, and downloads some samples. So the samples, at least intuitively at a first glance, the protocol looks like this. We choose a certain level of superblocks, a number of extra zeros that we desire. Let's say it's 5 extra zeros, in addition to the 10 that are required for validity. And we are only looking at blocks that have 15 zeros in their hash. So as a verifier, if I'm asking to synchronize and you guys are the provers, one of you could be adversarial, one of you could be honest, I'm receiving the samples from you, and what I'm comparing is really the count of superblocks that I have received from each of you. So this is similar to the way I do a length comparison in the regular underlying blockchain if I'm a full node, but here I just compare lengths of superchains. So I think, or I hope that gives some intuition about how this protocol works. There's a lot more detail, of course, on how to do the sampling more precisely, and the details, and there's quite a bit of hairy details, let's say, in the security proofs on getting it right. But for that, the interested cryptographers can look at our papers. I do hope, however, that this intuition is accessible to all the people that are power users of blockchains and have looked at a block explorer, and it makes sense.
Thank you. And can the same concept be applied to a platform that utilizes proof of stake for consensus, considering the mechanics are different and proofs are derived differently?
So proof of stake is a more complex protocol to compress in this way. We do have some work that speaks about stake compression, but one of the challenges there is that you cannot do this sampling as much as you can do in proof of work, as easily as you can do in proof of work. The reason is that in the case of proof of work, these superblocks occur with very predictable distributions. If I'm trying to mine, there's a chance I will get a superblock, and that chance can be defined precisely as a measure. In the case of stake, there's all these grinding attacks that can happen when somebody is trying to create proof of stake blocks. And proof of stake protocols that have been rigorously analyzed, such as Algorand or Urovodos, in these cases, there are ways to mitigate these grinding attacks, but this only happens at the zero level of the blockchain. If I somehow try to sample that proof of stake and I have some superblocks in proof of stake, that's not really helpful, because the adversary could, by simply grinding through their stake signature, create as many superblocks as they like. And those superblocks, their count will not be proportional to the adversarial power, as occurs in the case of proof of work. So the argument that I made previously, in which I said, look, the adversary with mining minority cannot create more superblocks than what is really rightfully theirs, this doesn't apply in proof of stake anymore. So the superblock technique for sampling is not really applicable to stake. We do have some protocols for compressing stake chains that are epoch-based. So in the case of stake, you would elect a sample block from each epoch that represents what is happening within that epoch, but you can't really compress further than that. And the reason is that proof of stake protocols have stake assumptions on how stake moves over time, how stake changes hands. And it's necessary for a verifier to know who is holding the stake so that they can verify the signatures and say, this is a block that was rightfully signed by the majority of the stake. So this really requires them to know the stake evolution. And if you limit stake evolution to a certain bound per epoch, showing one sample per epoch should be enough, but you cannot compress further than that. If I'm just booting from Genesis and I see fewer blocks than an epoch, I can't really deduce what is the stake distribution in the network right now. So I can't really verify such super light chains. So we don't have any super light stake clients at this time. There is no way to really build something like that to our knowledge. There are certain attempts to do this using zero knowledge proof constructions with snarks. One attempt, for example, is called Coda, but there are issues with that. For instance, there is a required trusted setup that we wish to avoid in these settings. So this I would actually mention and highlight as an advantage of proof of work protocols, that due to their simplicity of how the proof equation works and how mining works, and due to the fact that there is really no keys and no ability to grind, these superblocks really spring out of the protocol quite naturally. And this you cannot say about the case of proof of stake. So that's one advantage in Ergo being based on proof of work.
One question that I have related to this topic is, I believe, if I recall correctly, I think Alex Chaperno, one of the core devs at Ergo, 2017, I think he wrote a paper. Correct me if I'm wrong, I think it was called Twin Chains, about having a mixed proof of work and proof of stake system. And so something that this is kind of a thought that just came to me as you were mentioning proof of stake, is that this has never been done before, but theoretically, would it be possible to put a mixed proof of stake plus proof of work together on one blockchain and only have the proof of work there in order to produce proofs, which we can use, so super blocks based off of the proof of work, but still have the majority of the consensus be based on proof of stake? And so in such a way, since you're taking, in some way, you could say the best of both worlds in that case, where you can have the proof of work for the super blocks, but you still have the proof of stake for the majority of the, I guess, if you could do it 50-50, maybe 80-20, I'm not sure if that's possible. But has any research been done in that direction? And do you think something like that could be possible?
There's certainly some research that has been done in combining methods of consensus, such as stake and work, but there has been no research on how to build superblocks on top of such constructions. My intuition here, although I cannot answer definitively or categorically, is that this will be difficult to do. And one issue there is really, what are your security assumptions? If you define security assumptions appropriately, it might be possible, but really it comes down to whether you assume honest majority in the computational model, if you have honest majority by compute power. So if you do have honest majority by compute power, then definitely superblock is possible because an adversary cannot fake such chains. If your honest majority is just about proof of stake, then these can be really faked by an adversary. An adversary could create a fake chain. So even though there could be an underlying chain that shares proof of work and proof of stake, if you have an adversary who has proof of work majority, they could create a parallel chain or a large fork that just consists of superblocks and maybe fake proof of stake. And then the Superlight client could not really distinguish because they don't have the ability to check proof of stake. They can just check proof of work. So in this case, this would be difficult unless you impose an honest majority assumption by compute power. If you do have such an assumption, then you might as well go with proof of work. The question there is, could you create a protocol that, even though you assume computational power majority, maybe you don't put it to use all of the time, but you kind of slide it down a little bit and allow the stake to take over for whatever reasons they could be environmental or other. Generally, I would say it's difficult to create a superblock protocol on top of such hybrid protocols that combine work and stake, but we don't have a definitive answer on whether this is realizable.
So it would be a dynamic consensus model in some respect. Do NiPoPoWs then provide some advantages over proof of stake specifically? You mentioned about the ease of using keys and thus what?
Yeah, so about NiPoPoWs and keys and their advantages, well, the main advantage of NiPoPoWs is really that they can create superlight clients. And there is a quite precise mathematical definition that we follow when we speak about superlight clients. And that means that the gains in communication complexity are exponential. By that, I mean the number of bytes that I need to download from the network when I first boot up, it's exponentially smaller than the case if I was an SPV node. And the important thing in this exponential function mention is that these bytes don't really grow much at all when time goes by. So if Ergo is a protocol that survives 10 or 20 or 50 or 100 years, these NiPoPoWs will really remain about 100 or 200 kilobytes, regardless of the fact that this blockchain could have a tremendous history of money transfers of worth just 1 century. In the case of Bitcoin SPV, even in the SPV case, you just need to send the headers that belong to every 10-minute interval for that 1 century. So that's what we mean by an exponential improvement. In the case of stake, we don't have that. So for stake, you still need to send one representative per epoch, which means that after a sufficient number of years have passed, these proofs will get larger. They just grow by a certain rate per day or per year. But in the case of proof of work, you don't have that growth. It could be that 10 years have passed and you don't see any growth at all. It's just very, very minimal. So that's one big advantage of super light clients that have these exponential gains.
And where would the idea of cross-chain communication factor in with all of this? How does the concept of NiPoPoWs enable an efficient transfer?
Thanks, Ollie, for asking me this, because that's one of the most interesting topics. It's one of the most exciting applications of NiPoPoWs here, because the super light applications, I mean, okay, we've seen SPV clients, we've seen some efficiency gains there, and the exponential gains don't really hit us until many years have passed and these chains have grown. But cross-chain communication and interoperability is a very timely topic that has applications immediately. So what this stems from is the fact that in addition to Superblock or Superlight clients consuming these proofs of work, these proofs of work can also be consumed by remote chains where you have some smart contracts that function as verifiers for NiPoPoWs. So you can think of a smart contract. Suppose you have a smart contract in Ethereum or Cardano or EOS or Ethereum Classic or Waves or whatever platform has smart contract abilities. Then you could construct a little program in the form of a smart contract that functions as a node for Ergo. And what that will do is it will not really participate in the network, because a smart contract cannot really have network connections, but it will have the ability to receive data that is submitted to it in the form of transactions that are hinting to what is happening in the Ergo blockchain. So any friendly but untrusted node that is monitoring Ergo and is willing to submit such hints to the smart contract will allow it to process what is happening in Ergo. And the critical thing here is, well, first of all, because this is really a verifier that has comparable security to SPV and full nodes, there is no way for an adversarial user to create a transaction with fake data, submit it to the smart contract, and convince it that something wrong is happening, some lie, let's say. You cannot do that because this is really equivalent to a verifier node. This smart contract then can maintain some state of what is going on in the Ergo blockchain, or even without maintaining state, just by looking at what is given to it, it can deduce and take decisions based on what is happening in Ergo. And what I mean by that is questions such as, did a transaction take place? Did a particular account change its balance? Is there a UTXO in the case of Ergo? Or did a particular script execute in a particular way? So you can have really very advanced interactions between these two chains. Anything that a smart contract can read from Ethereum, if it runs within Ethereum, it can also now read from Ergo, even more actually than what is available to Ethereum within itself. Now you can read it from a remote blockchain. And this allows you to build many things. One example is remote ICOs. Another example is DeFi, the decentralized finance applications, in which you have derivatives that can connect different chains. And you can have, for example, financial securities that function within Ethereum, but they securitize tokens that live on Ergo. So you can have all of these nice, very interesting interconnections where things play together very nicely. And of course, you can have also things like games and micropayments and all sorts of things. Of course, also simpler things such as atomic swaps. But you can definitely see some contract that says, okay, I will breed a CryptoKitty only under the condition that a payment has been made in Ergo, and that's more than an atomic swap. It's information transfer, like genuine. It's really a genuine protocol in which you transfer information. You can think of it almost as HTTP between blockchains, except there's some assisting parties, there's lots of moving parts, there's smart contracts, and it's completely decentralized, but really it's a data transfer.
Something related to this, one thing that I was wondering is whether NiPoPoW proofs are fungible. So that let's say we have two blockchains and they each have NiPoPoWs. Can we have one verifier that verifies both? Or does each one have to be customized with a custom verifier? And then related to that, yes or no, is it possible to then have an efficient primitive on blockchains? So let's say we have a blockchain that wants to be a NiPoPoW verifier, so it has interoperability. Would it make sense to make that a base primitive rather than on the smart contract layer? And so that's related to the fungibility, because that would obviously make it a bit easier.
Yeah, that's a very interesting question. And yes, the answer is yes, generally. The verifier is quite generic. It is parameterized by certain things, but the code itself is pretty generic across verifying any NiPoPoW. So let me speak about the parameters that it requires. The first parameter is a hash of the genesis block of the remote chain, because we need to know what chain we're speaking of. I cannot compare the longest chain of Ethereum with the longest chain of Ergo. I have to compare apples to apples. So I have to say, okay, if I'm looking at two Ergo chains, this one is the longest, but maybe there has happened a lot of proof of work in Ethereum that does not concern me. So that's one parameter. The second parameter is the block format, and it's a little bit more closer to the engineering decisions that need to be taken here. And that pertains to, most importantly, the hash function in use for proof of work. So Bitcoin verification will be different from Litecoin verification due to the different hash function that connects blocks. And then lastly, along this same route, you have to have some parsing that has to do with a specific chain in terms of how a block is structured. For example, in Ergo, the way that the chain has support for NiPoPoWs is that it's interconnected. So blocks have additional pointers to previous blocks. One question there is, where are these pointers stored? Are they stored in the block header, such as in Ergo, or are they stored in the Coinbase transaction, such as in a chain that would adopt a soft fork implementation of interlinking? So these little details need to be taken into account for the verification, but these details really come down to a pretty simple verification function that does some block parsing. So for the primitive itself, this could be implemented as an op code for the blockchain itself. And that would make it quite powerful because it would allow any incoming data from any source. However, it would have to be parameterizable first by a string parameter that is the hash, and secondly by a little lambda that does the business of parsing the block and extracting the interlinks, which is a little bit more complicated. However, the primitive itself that checks whether the samples are okay, whether the proof of work is sufficient, and does all the hardcore work of comparison, that would have to be the same. And that's why it would make sense to make it an opcode if you don't want to have a fully fledged Turing complete smart contract language for whatever reason.
Great. And you mentioned before about the stringing together of headers, which subsequently we would have less data to transfer, more bandwidth to play with. What consequences would we get of this, apart from potentially a higher transaction per second between two chains?
So the main benefit in having very, very short proofs when you talk about interoperability is that it's very efficient to verify these things because you don't have a lot of data to look through. And this verification can be actually implemented in a smart contract that is gas efficient. So if you look at an SPV verifier that has to go through the whole chain headers, this is really quite impossible to write in a single smart contract call. If you try to give the whole Bitcoin blockchain of 32 megabytes or 60 megabytes, I don't know how much it is, the block headers, just the block headers, right, without any transactions, if you try to give this to an Ethereum smart contract, it will run out of gas before even processing the input parameters very quickly. And even in the case of NiPoPoWs, because the gas limits of Ethereum are so restrictive, in order to implement NiPoPoW verification in Ethereum, we had to do quite a bit of engineering work. In fact, this last summer, we have a paper in the AFT conference, AFT 2020, in which we just describe how to make NiPoPoWs gas efficient so that they fit within an Ethereum transaction. And there's a lot of engineering work that goes into that, including modifications to the underlying cryptography of the protocol itself, because the original protocol was designed for Superlight clients and not for cross-chain consumption. But just the fact that this is an exponentially smaller data structure than the blockchain itself allows us to really build gas-efficient smart contract calls like that. And that's what enables cross-chain interoperability. Without this, you wouldn't really be able to do that. You would have a blockchain. If you had just SPV, you would have a blockchain that would need to verify every single block of the remote chain. And that's really not practical. It's not very pragmatic to expect Ethereum to include all of Bitcoin and all of Ergo, right? So you want this kind of isolation between the chains. You just want to transfer enough information to be able to take a decision about a cross-chain event, but not the whole history of proof of work when it occurred remotely. So that's where it comes in.
And pushing ahead, there is a basket of concepts encompassing NiPoPoWs and some that even contrast the solution for similar predicates. For one example is Fly Client, which also proposes a method of achieving Superlight clients. I was wondering what your thoughts are upon this and what solution would be better to choose out of the two.
Yeah, so my opinion on Fly Client. So Fly Clients are a NiPoPoW. They are inspired by our original ideas on NiPoPoWs in which we define the primitive, but they are a different solution to the same problem. So our solution is a superblock-based NiPoPoW. Their solution is a different way of sampling blocks. They don't use the superblock construct, but it's still a NiPoPoW because it's a non-interactive proof of work. The way they do some sampling is based on a Fiat-Shamir heuristic, which is a different cryptographic construction. And there's a few differences. So first difference that I would identify is that Fly Client seems to be, for now, for small chains, it seems to be practically a little bit smaller than NiPoPoWs, than superblock NiPoPoWs. However, asymptotically, NiPoPoWs are generally better. So there's a difference in the asymptotic complexity of how these proofs grow, and given sufficient time, there is a small difference in factors. So you can say, I mean, that's maybe a little bit too mathematical, but in the case of superblock NiPoPoWs, you have a log factor or log factor, while in the Fly Client, you have just a log factor. And that makes just a little bit of difference. So that factor is almost a constant for superblock NiPoPoWs, but you do have some growth in the case of Fly Client. And this will appear once blockchains start growing sufficiently. Another difference with Fly Client is that they were the first paper to propose NiPoPoWs that work well with variable difficulty targets as well. So the targets in any blockchain, any proof of work blockchain such as Ergo, they change with time based on how many miners are on the network. And in the case of Fly Client, they argued that their protocol is secure even if the target changes. In the case of NiPoPoWs, our original analysis had been in the static model in which difficulty remains constant. But our latest result prove that our construction works also in the variable difficulty case, even with superblocks. And in fact, there is the exact same construction that we had proposed for the static case also works in the dynamic case, along with a couple of different constructions that we propose that are all superblock based. So the nice happenstance about that is that Ergo already has support for these variable difficulty protocols, even though when Ergo was invented, Fly Client was not really as mature. It was not a peer-reviewed paper at the time. So that's kind of a lucky coincidence for Ergo that they have adopted this kind of interlinking that supports superblock-based NiPoPoWs because they also can verify variable difficulty now. To be honest, the Fly Client construction is quite nice. So it's something I like a lot. Their variable difficulty handling is nice. Their construction is quite simple. So generally, it's a protocol that I favor a lot. Given the current way that Ergo interlinks their chains, Fly client cannot be implemented in Ergo. So Ergo can only implement superblock NiPoPoWs. And the reason why this is so is that in Ergo, the header points to the most recent superblocks of every level. So it's very closely related to how superblocks are generated. In the case of Fly client, these pointers can change and they can point to any other location in the chain. So you kind of need to have a pointer from every block to every other previous block. And that's not something that Ergo implements. And that's actually one of the factors that comes into play when you analyze the asymptotic complexities of superblocks and Fly client.
The next section of the podcast takes a look at an idea called log space mining. This idea isn't actually published yet, and as such makes you one of the few that have had the chance to listen and review them. In a way, this is an exclusive. Enjoy.
But one of the most interesting applications of NiPoPoWs and the interlinking that has been done in Ergo is that there is a structure that can be built on top of NiPoPoWs that cannot be really built in Fly client. And that comes from the fact that NiPoPoWs have a sort of determinism, and Fly client is a little bit more non-deterministic. So let me give a little bit more detail. And this comes to a newer work that we have. It touches upon a newer work that we have pending, which is about logarithmic space mining, log space mining. So this is something that is possible in superblock-based NiPoPoWs. And the requirement there is that these NiPoPoWs have to be online, what we call online, or online NiPoPoWs, ONiPoPoWs. So in this case, what we're using this term for is, well, it comes from the 60s, the algorithmic literature of the 60s, where online just means that you have a data structure that can be updated very efficiently when new data is available. So it does not come from the onlineness of the internet, but it comes from being online, expecting new data to update your data structure. So in the case of NiPoPoWs, we have a very, very nice property that makes them online, and that is the following. If you have a NiPoPoW for an existing chain, and then a new block is mined on top of the underlying chain, then you can create a new NiPoPoW for the new chain very efficiently. And in fact, what you need is just the old NiPoPoW and the new block. And that's the reason why that is because the way that you sample superblocks is very, very specific. If something is a superblock, it remains a superblock of that level for eternity. In the case of Fly client, because the sampling changes every block, your sampling might change for the whole past history. And so you must have the whole blockchain in your hands in order to regenerate a new Fly client NiPoPoW. So in the case of superblocks, you have this nice property that the prefix that you have generated your NiPoPoW on is now useful for the new block that is being mined. And that means that if I'm mining blocks, I can mine blocks on top of NiPoPoWs instead of just chains. If I have a NiPoPoW, I can use it to just mine on top of it. The NiPoPoW has the most recent block towards the tip. So I can use that to mine on top of that, create a new NiPoPoW, and distribute that on the network. I can broadcast that on the network. And what that means is that if I want to do that kind of mining, the miners can just keep NiPoPoWs and that's all. The miners can mine on top of old NiPoPoWs, create new NiPoPoWs, exchange NiPoPoWs on the network, and only store such things. You don't need to store blockchains anymore. Blockchains are useful because they contain transactional history. So if you want, you can have archival nodes that maintain this history. But for the purpose of knowing who has how much balance and the current UTXO, it's not really needed to have the whole transition between UTXOs in the past. So that's not really required. So this is a new paper that we have coming up, which basically enables this new form of mining, which is super light mining, in which you don't really need to store the whole history to do some mining. And even if you're booting up a new miner, you don't need to download the blockchain. You can just download a very short proof and start mining immediately, and even start verifying transactions. So it's not equivalent to an SPV miner where they don't look at transactions, because you can hold the actual current UTXO and you can verify that this is the current UTXO because it is confirmed by an NiPoPoW. And then when you see transactions, you can check whether they really evolve the UTXO correctly. and produce a new NiPoPoW. So its security is quite comparable to a full node in the honest majority model. So that would be like a significant difference, I would say, between flag client and super block-based proofs.
So as you were saying earlier right there, the flag client is effectively a NiPoPoW. And going back to the last question I had of having a generalized verifier. Well, the difference between these two, right, is the sampling method, and that has, further effects down the line, like what you're saying with log space mining. And so, two questions that come up from that I have is, do you think, or do you know potentially, that there are other sampling methods, and this is an area of research where you can keep coming up with new sampling methods, or there might be some limit, but there's still some potential, and that each new sampling method may have other phenomenological effects, you could say, on top, which can produce something like log space mining? And related to that, then, if yes or no, can we have a generalized verifier for every type of NiPoPoW? So whether it's superblocks, fly client, or anything else that comes out for the future for sampling?
Yeah, so it's difficult to tell if there will be further methods of sampling. These two really do partition a little bit the space. On one hand, with superblock NiPoPoWs, you have a deterministic method where these come up very naturally from the mining process. You could have superblock-like sampling methods that use some different property to elect block samples. For example, you could look at the last zeros instead of the first zeros, but really mathematically that's quite equivalent. And then, so that's kind of a deterministic protocol in the sense that while the mining process is random, once the mining has been completed, these samples do not really change. On the other hand, in the case of fly client, you want to do some sampling which changes for every block. So it's a kind of non-deterministic way. So these two protocols really do partition the space a little bit. You have deterministic NiPoPoWs and then non-deterministic NiPoPoWs. And both of these offer benefits, each kind of different. There's certainly the possibility of having different deterministic and different non-deterministic protocols that make small changes to the way they do sampling, but I don't see them having any benefits over the existing ones that we have. Whether it's possible to have a third kind of protocol that kind of is a hybrid between the two or is a completely different thing, I don't really know. This is maybe up for research, as well as whether these things can be optimized further and maybe made constant space instead of logarithmic space. There is some research there in the topic of using snarks or using starks to create constant size proofs of proofs. In the case of snarks, it's a different model because it requires a trusted setup. In the case of starks, as far as we know, while the proofs are constant size, it takes a lot of time to build such proofs, even for small chains. So maybe the time that it takes to build it is a constant time, but if it's a few years to just create a proof, then this is not practical. So this might be another category that brings down the gains to constant instead of logarithmic, which is quite impressive. So that's an open area of research. Whether we can generalize the opcode here, I'd say there's some differences between fly client and superblocks. They use a different tree structure to hold blocks. So in our case, we use a simple Merkle tree where the interlink pointers are stored. In the case, and that Merkle tree has a logarithmic number of leaves, so its height is log. In the case of fly client, they use a kind of different structure, which is a Merkle segment tree, in which you can actually ask questions about segments within that tree and compute an aggregate function on top of them. And what they're using this is to sum the difficulties of a segment of the tree without actually looking at the tree. So it's a very nice combination. I actually find very elegant that they combined a cryptographically authenticated data structure, such as a Merkle tree, with a more traditional data structure from the 60s and 70s, the segment tree, which has traditionally been useful for things like solving complex range queries, algorithms, and such. So given that there's these inherent differences in the data structures that are used for the pointers, I'd say it would be a little bit more difficult to generalize these opcodes. Maybe we can look at some lessons learned from functional programming languages to maybe generalize them into some category theory structures, maybe a functor for blockchains, let's say, where you can traverse a blockchain in a more generic way. But that would be quite a generalization. So I would say a simple opcode that is able to parse both of them will be difficult to be constructed, at least in like more traditional programming semantics.
NiPoPoWs definitely seem to bring a lot of lucrative opportunities from what you've just discussed. In itself, I think that could be another episode up for grabs within that content. But for a blockchain that is already live and on mainnet and is looking to implement NiPoPoWs, how would they go about this? Would it be a soft fork or a hard fork? How could it be done?
So for an existing blockchain that does not have NiPoPoW support, so we are excluding Ergo here because this already is implemented there. If you're looking at, let's say, Ethereum or Bitcoin or Litecoin, I know for a fact Litecoin is interested in, for example, implementing this. There's a few routes. One would be to do a hard fork in which you would implement a structure similar to Ergo by modifying the block header to include interlink pointers. Another way would be to do a soft fork in which you would change the Coinbase transaction and replace some of the commentary part of that with the root of a Merkle tree of interlinks. Another way that we have proposed is a velvet fork, which is a different type of forks from hard forks and soft forks, in which you ask for a consensus change that is adopted by a portion of the miners. And these new miners, they mine by adding some extra information into the Coinbase transaction. However, even if a miner is upgraded, they accept both old and new blocks, which means that now, even if somebody's mining old blocks, they will still participate in growing the blockchain. And so now your blockchain will look like a series of blocks, some of which will have the upgraded data and some of which won't have the data. So you have a blockchain, you can think of it as a colored blockchain where some blocks are black and some are white, or we call these velvet blocks, the blocks that have the additional information. One of the nice results we have for NiPoPoWs, superblock-based NiPoPoWs, is that it's possible to implement this interlinking through a velvet fork. And having a velvet fork really does give some benefits in doing cross-chain communication and building super light clients, as long as a significant portion of the miners participate in that velvet fork. But that portion of miners doesn't really have to be a super majority, such as a soft fork. You don't need 95%. If you have 50% or 40%, you can have very meaningful upgrade that offers good security and good performance. Now, the performance incurs a penalty. The fewer miners adopting the protocol, the less performant your protocol is. And also your adversarial bounds on what an adversary can do to produce a contesting NiPoPoW are different. So if you have just the 1% of your miners, of your honest miners upgrading, then your NiPoPoWs become suddenly 100 times larger. While if you have a 50% of miners adopting NiPoPoWs, then your NiPoPoWs are just twice as large as if you had, as compared to having a soft fork. In the case of adversarial bounds, your adversary must be bounded to 1/3 of the upgraded population. So if 50% upgrades, then you can tolerate a 17% adversary. If you have just 30% upgrading, then you can tolerate just a 10% adversary, which is maybe something that you're willing to live with or not, depending on your threat model. The nice thing about that is that we can actually quantify that. We can look at the network, we can observe the blockchain, we can see how many blocks are velvet blocks, and then we can take our decisions on whether we want to move a huge amount of money on a cross-chain DeFi transfer, or whether this is still unsafe until more people upgrade. And it can also be kind of a gradual upgrade. So we can launch a Velvet fork and we can say, okay, whoever wants this, they can start contributing to that. We can see a 10%, and then after a year, we can see 20%. And the security is kind of slowly growing up and the performance is slowly growing up. And this is quite different from the sudden upgrade that a soft fork or hard fork is. So that's one method that is perhaps more preferable by various chains. I should mention, however, that Ethereum does have a hard fork proposal for including some interlinks that support both Superblock NiPoPoWs as well as Fly Client. And this is something that might happen at some point. And also Zcash has performed a hard fork, which includes support for both Fly Client and Superblock NiPoPoWs by including the appropriate Merkle trees. So all of these variants have been tried in real systems. Let me say also that some people from my team have, Kostis Karantias in particular, he has implemented a Velvet fork on top of Bitcoin Cash testnet. So that might not be transferring real money, but we have seen that it's actually possible to do on a real chain with real blocks and real transactions outside of the laboratory where we play, with a few prototype blockchains. So it's definitely possible to do, and we've seen everything. We've seen starting from Genesis, using a soft fork, using a hard fork, using a Velvet fork.
So outside of the focus from looking at layer one, is there any other areas or implementations we could expect to see NiPoPoWs appear in? Maybe a consideration might be in sidechains and how that may factor into all of this.
Yeah, so sidechains are really quite related to what we discussed about interoperability. They're really quite the same thing in terms of technology on how data is exchanged. The only difference in the sidechains, at least the way they were envisioned by Bitcoin pioneers, such as Bag and Maxwell and Miller, they are chains that are child chains to a parent chain. So they come into life by forking from a parent chain, then going on for a bit independently, maybe from a different genesis that inherits from the parent chain. And then they can be also code forks of the original blockchain, making some changes in some of the features, adding some new features, experimenting with a different consensus model, and so on. And the idea there is how you use these to try out new features. So you want people to be able to move their money back and forth between the main chain and the child chain. But since we are able to do that in heterogeneous systems, it's much easier to do in homogeneous systems where the child-parent relationship comes into play. So with NiPoPoWs, as I described, you can have heterogeneous communication. You can even move data from proof-of-work chains to proof-of-stake chains, let alone moving data between chains that run almost the same protocol. So the idea of creating a side chain to experiment with some new feature without actually having to create a fork in the main chain, this is really doable with NiPoPoWs because all you need to do is create that child chain and then move data back and forth using a NiPoPoW mechanism. One of the challenges there is how do you secure the child chain by ensuring it has sufficient proof of work or proof of stake. And that's kind of a different topic here on whether you want to do merged mining of some sort or merged staking. And additionally, what are your security assumptions there? For example, one of the concerns of Bitcoin developers, such as BlueMat, is whether the child chain, the side chain, will face adversarial attacks from the maintainers of the main chain because they don't want to see these new features. They see it, that they could be like maximalists and they just want to keep their mining power on the main chain, so they might attack the child chain. Another concern there is what are the game theoretic analysis at play between child chains and parent chains when you have a network of miners that has incentives to attack the network so that they can steal money, in which case you might not be able to make the honest majority assumption anymore, and you want to take an honest rational assumption in which sorry, not an honest rational, but a majority rational assumption, rational majority assumption, in which your majority is rational but not honest, in which case these chains, because they can store a lot of value, could be high targets for miners that are rational, but not necessarily honest. So there's several questions to ask there, just because it's so easy to move mining power between the two since they follow the same protocol. And we've seen that instance in chains that are heterogeneous. For example, Bitcoin and Bitcoin Cash that are kind of different protocols. They're not supposed to be child parent chain, but miners do move around and they move their mining power from one chain to the other based on how much money they can have. One of the game theoretic questions here is, what happens if you have a child chain, and can you fake NiPoPoWs and such proofs if you give them sufficient incentive to move around their mining power and you don't have honest majority anymore, which is the cryptographic treatment. So there's a lot of game theoretic questions that remain open in that area, and they can be quite tricky. However, as a basic protocol, I'd say because heterogeneous communication is possible, homogeneous communication follows, at least in the cryptographic layer.
Considering how, together with that, we could exercise NiPoPoWs, what would the operation actually look like when functioning? So, for example, how would two chains actually communicate with each other? Would there be an entity on each chain that enables this? Or would it be something similar to an API just so they can communicate?
Right. So first of all, one of the properties that we have remained focused on and have achieved in these protocols is what we call miner isolation. And miner isolation means that the miners of each chain do not really need to know at all about the other chains. Some other protocols, such as the Waves protocol, calls this agnosticism, blockchain agnosticism. We've also coined that term in a previous paper that we have on proof of work side chains. This is a basic property that we want. We don't want miners on Ergo to also have to run Bitcoin full nodes. That would be terrible, and it would not be adopted. So imagine having hundreds of cryptocurrencies communicating with one another. You would have each blockchain node required to run 100 of different nodes, and that would completely kill decentralization. So this is not something that we can afford. The way that functions is that the miners maintain their own chains. They verify their own smart contracts and transactions and UTXOs and what have you. And then the users that want to transfer the information, what they do is they run light clients on both chains. It could be SPV or it could be superlight. And what they do is they observe one chain for transactions of interest. It could be a transaction that transfers some value on that chain. And then they want to submit that information to the target blockchain, to the destination blockchain that will process that information. So the destination chain already has a smart contract that is ready to receive that information. Now, the user that has performed the transaction that is of interest to them, they can use their Superlight client or just SPV client or full node to create an NiPoPoW to submit to the smart contract. So this is not done by a miner or an external entity or any federation. It's not centralized at all. The users themselves who have interest in running this protocol, in particular, the user who would benefit from this transaction executing on the target blockchain, they can collect and submit the data. And from what I said before, they're not allowed to lie. If they lie, they will be caught. And in fact, we even have a small incentive mechanism in which we crypto economically can ensure that such users are slashed appropriately in case they submit a lie, and the person catching them is paid appropriately. So this is something that we also describe in our protocols. And we call these nodes friendly but untrusted because they help out, but they cannot really make the protocol fail even if they want to. So as long as there's a few such actors in the network, and we don't need to assume anything beyond rationality because they are paid, this protocol will function correctly. So to answer your question a little bit more succinctly, the data transfer is done by the person interested themselves, in particular by their node, their wallet. And in case they're caught, there could be some friendly nodes, but are trusted, that help out to figure out such problems, and they collect a payment in that case, which is paid out by the adversary who made the incorrect claim.
And through these nodes, could we thus conduct an ICO as such, with distribution on one chain and payments taken from another chain? Maybe even distribution across both chains?
Yes, definitely. If you have a destination chain which is feature rich enough to create tokens with nice features, it could be a smart contract enabled chain. It could be a faster chain. It could be any nice features that you want. But that chain does not have sufficient capital to raise in an ICO. You can make the payments for that ICO within a different chain and then receive the tokens on a different chain. So you can have a source chain in which capital payments are made. That could be, for example, Bitcoin, in which a lot of people store their money for long term. And then you could have another chain which is more feature rich. It could be, let's say, Cardano, Ethereum, Ergo, or is faster, in which you generate and pay out the tokens. So you do fundraising on one, but you pay out the tokens on the other. And you can easily imagine a centralized version of this where there's an entity that collects the money and issues the token, but using NiPoPoWs and cross-chain transfers, you don't really need that central party. You can now ensure in a smart contract that this is performed correctly. One of the nice things about that is that now you can denominate your ICO tokens in the base currency of the source chain, which would be impossible otherwise. So you can say, I will issue tokens on the Ethereum blockchain, but the price per token is so many Bitcoins, for example.
And taking this even further, could we have a decentralized application that is potentially scattered across two chains and execution as such?
Yeah, definitely. So you can do fundraising from multiple chains. You can do tokenization on other chains. You can even have games and micropayments, moving money around, and certainly also DeFi applications in which you make payments on one chain or multiple chains, and then you have derivatives, financial derivatives on other chains. One such example that we have described in a recent paper, we call the paper Smart Contract Derivatives. One such example is providing insurance, in which you have a chain that pays some insurance payout in case something goes wrong in a remote blockchain. So you can say, oh, I'm raising this ICO money on the Ethereum blockchain. In case I don't raise sufficient amount of money, or in case there's an insufficient number of backers, or there's too few whales, or whatever condition you want to impose, I want to get paid out in Ether, let's say. Or you can really connect any chains there, or you can even have bundles or baskets of various tokens that you have conditions on that they behave together. You can have a basket that you say, okay, what is the value of this basket that includes Ether and Bitcoin and Monero and whatever, what have you. And then you can say, okay, if the value of that becomes high or low, here's an option, here's a future, here is an insurance on that. All of this can be nicely tokenized, and you can have decentralized finance derivatives essentially on top of all of these things, and they can be nested, they can be composed, they can be nicely interconnected, involving multiple chains and touching on all of these.
Great. And is there potentially any technologies or functionalities we see on ledgers today that would be replaced by NiPoPoWs? As you mentioned with the NiPoPoWs on top of NiPoPoWs, in my mind that sort of suggests that functions such as pruning and sharding might be unnecessary through that method.
So generally, I would not dismiss sharding and pruning so easily, because they have like various applications, various different security models. As I said, for example, there's incentives at play that must be studied. But definitely, at least at a high level, for example, in terms of sharding, one ridiculously straightforward way to do sharding is to have different blockchains and have NiPoPoWs for communication between them. Because shards are homogeneous, you might have better protocols, but that's definitely like a baseline that you can use. So yeah, you can definitely say, if I have shards, their communication can be based on NiPoPoWs. Given that they're homogeneous, maybe I can do better. But for comparison, that's definitely a baseline all the time. So that's another technology on which NiPoPoWs could be used, at least as a benchmark.
Thank you. And to offer some conclusion for what we have discussed today, as I'm sure we've incubated quite a lot of curiosity from what we've gone over, let's finish upon thinking more towards time to come. How do you envision the future of proof-based blockchain interoperability?
So one of the visions that I have that I really don't know if it will be realized is developing a standard in which multiple blockchains can participate, maybe forming a standard for the ecosystem in which there is a standardized way in which blocks, transactions, and so on can be communicated across chains. And if that is built and multiple blockchains participate in that, I think this can actually increase the value of the whole ecosystem together. Because really there's a lot of network effects from people using Bitcoin or Ethereum or Monero or Ergo. And a lot of the value of each of these chains is kind of bound by how many other actors I can communicate with or act as counterparties with. So if all these things are connected through a common standard, this really increases the whole value of the whole blockchain ecosystem. Suddenly my Ergo can be used not just for paying within the Ergo blockchain, but for any blockchain. So suddenly value is increased across the whole space. So that would be nice to see and see such a standard being developed. And of course, this requires a lot of coordination between the blockchains. There's currently a lot of different interoperability endeavors, from Waves to Polkadot to Axelar to all of these different protocols that are taking a different stance on how to do these things. It would be nice to have a standard that all these could participate in and to have multiple blockchains interconnected with one another. And if this becomes the standard and most blockchains implement this and it becomes a user requirement from the users and they want it to happen, this will create a big ecosystem where everything is connected. And then every blockchain can offer its own features, but then my money is not really bound to one. I can move it from one chain to another easily. Another question there is, how do we do this in a user-friendly way? Because all of these, right now, the research papers, okay, there's a lot of implementation as well. There's code in Ergo that does this, but there's no user-friendly way to do all of these things that we describe. It's kind of just wishful thinking there. So it would be nice to see this vision realized in user-friendly applications where wallets can do all these kind of data transfers, information transfers, value transfers between different blockchains, so that end users can do this really easily and they can understand what's going on without having to, be experts in the science and the technology.
And on the topic of data feeds, current solutions use trusted federated oracles who report actions from one chain to another. Can NiPoPoWs and other proof-based solutions be used in a trustless manner at all?
Yes, NiPoPoWs are completely trustless. They use this functionality of friendly but untrusted nodes. There's no need for oracles. And the only big limitation is that this only pertains to chain-to-chain data. If I have one chain, I can trustlessly report that data to another chain. They cannot replace oracles for real-world events. They're not designed for that. They're proof of work only and not other things. So yeah, they're trustless, but for their purpose, let's say.
Related to that, is it possible to accumulate NiPoPoWs that have proofs from other chains? So let's say you have 3 chains and you want a proof from chain A on chain C. So you put chain A proof on chain B, and then that data from chain B is then used in a NiPoPoW for proof passed on to chain C. Does that work?
Sure.
Okay.
Yeah, you can do that. These would be nested NiPoPoWs. They don't. So you have to incur the size penalty for both, even though they're small. So they're kind of added. They don't compress together. But yeah, you can have a NiPoPoW about a NiPoPoW. So you can say, okay, there was this NiPoPoW that was received in the smart contract. Here's a NiPoPoW that proves the fact that that contract received that NiPoPoW. So you can do that kind of recursive nesting of NiPoPoWs, definitely.
Thank you. And there we have it. Everything we have discussed today provides a conclusive definition of interoperability between blockchains. Thank you for putting the time aside today for this rundown and for all the work you've done to enable the functionalities from NiPoPoWs. I think a nice thing for the viewers watching to consider between each episode is what will define a blockchain success within the future. Will it be one where dApps are isolated to the protocol they operate on, or will it be a set of platforms that create a harmony within all this chaos, interconnectivity? Following on, is there anything else you would like to close with for today, Dionysis?
Well, I just want to thank you, Ollie and Robert, for having me today. It was a wonderful discussion. Thank you for very interesting questions. I hope the audience finds the technical discussions interesting here. And I'd like to also thank you and the whole Ergo community for developing this wonderful cryptocurrency and for adopting our ideas and being pioneers in the space. It's great to see. And I'm really looking forward to seeing all these technologies implemented in Ergo in a way that can be used by end users, including the super light clients as well as cross-chain interoperability. So that's an exciting time to, be alive in the space and watch these technologies evolve.
On that account, all the technical papers that have formed the foundation of what we've discussed today will be referenced. And for those watching and listening, until next time, thank you.